Good morning, everyone. I'd like to start by thanking the organizers and specifically Core of Signals for inviting us and giving us an opportunity to present our ideas over here. First, a brief introduction. I'm Kandasamy. I take care of software development in Signalchip. Signalchip is one of the very few semiconductor companies in India. We are a startup company started in 2010. We focus on complete system on a chip chipsets for wireless communication, and so we work on physical layers for various communications and using them for military, and also securing them for military use is something which on which we have quite a few thoughts to present on. Okay, so I think we have been having this session for the last 2 days, and you have noticed that there are a lot of sessions covering the broad trends, focusing on the digital army trends as well as the global communications. And you can see that in today's session we are going a little bit more detail into the technical areas, specifically focusing on security as well. So similarly, we are also going to, my presentation is going to focus on the physical layer security. I think just at the start of this session, Kapil Jaswal was just mentioning to us that it's a challenge to secure wireless networks, because unlike wired and physical networks, where at least there is a step of going and getting access to that, but in the case of wireless networks, you are essentially broadcasting your communication, right? So anyone who is in that area who can receive a signal can receive it and then will be able to decipher. Okay, so one of the basic steps which you can do is to encrypt the information which is being sent. Okay, instead of just sending it in plain text, we encrypt. So what is the encryption? Okay, so using a key which is kept secret. Okay, so you encrypt the text which is you scramble the text so that it becomes a ciphered text. Okay, what is indecipherable? Okay, and then it is transmitted over the air. Now at the receiver, the same encrypted text is received and then it's decrypted. Now the decryption requires a key. Now it could be the same key which was sent during encryption, or it could be a different key. In those two cases it is called symmetric and asymmetric key. But once you are decrypted, you will be able to get the original communication. So this is the basic step which can be done. Okay, so but where exactly does this fit in a typical communication network? Okay, so a bit of terminology, and we all would have learned that communication networks use a layered approach. So they start with the layer 1, which is the physical layer, that is the medium. Okay, so in case of let's say something like Ethernet, that is the wire over which it is going on, and in case of wireless networks, that would be the radio medium which is going over a specific frequency. So that is the physical layer. That's what the physical layer deals with. Just above that, you will have the L2 or the link layer, which manages a higher level data link. Okay, and you will have layers and so on. Okay, but our focus will be primarily on these. Okay, I will also like to mention that a layer can contain multiple modules. Okay, it's like whatever is the functionality of a layer is often done in 2-3 different sub layers or modules. So again, at each layer, depending on the type of data which is going on, we call it as an associated channel. Now please note that this is not directly related to actual radio frequency channel. Okay, the way you would refer it to in various networks. This is like a collection of information. So for example, if you take LTE, there is something which we call as the physical downlink control channel. Okay, so downlink control channel is something where instead of actual data, the resources and other details about how to use the network to actually transmit your data comes. So it's kind of a metadata. It doesn't contain your data, but it tells you how using this network you can send your data. So that's an example of a control channel. Okay, so in this presentation we will be using this terminology, so that's a refresher for that. So let's again go in a bit of detail. So in these kind of layered networks, So how do we have encryption? So you have this L2, L1 and L2, and you have multiple modules over here. So this IP packet is essentially the user data. The IP packet that you see there is the user data which is coming over there. And in the first step itself, it kind of gets encrypted. So as soon as it enters the network, it gets encrypted. But what is interesting is what happens after that, okay? So after that, if you see, each layer is adding its own information, okay? So you have this RLC module which is adding its header and then there and so on. And if you see in the actual physical layer, these additional information which has been added does not really get encrypted, okay? So this unprotected information can be used by an attacker. So we will see a little bit of detail into what exactly constitutes this information later. But it's very clear that what we would ideally want is for the entire thing to be encrypted, okay? So what are the consequences of this unprotected information? For example, you can have a denial of service attack, okay? By just simply sending spurious requests on some entry channels. So what are these entry channels? If you think about a fortified area, like this would be like the gate, okay? And what is a spurious attack? Instead, there are so many false people coming and just ringing the fort and going back and clogging the area such that the legitimate users can't come. So that would be one kind of example. Why? Because in the radio network, they know where the equivalent of that door for the fort is present and then they're coming and knocking, okay? Because they know some amount of information is not encrypted and they know all these details, okay? So then they can also monitor these control channels. I already said these control channels actually tell you where to go and which radio resources to use, as well as it can tell you the channel quality that each user is facing, and sometimes just which users are getting data itself could be a sensitive information in the defense context, okay? Additionally, they can also use this to selectively disrupt, okay? That is, you target only a particular user's thing. As he was talking about the hidden malware, here there is an attack which is going on and you don't even know, because only specific users are, the entire network is jammed, then the people operating the network will realize that it's happening, but if targeted disruption is happening, you may not even notice the disruption is happening. It's kind of hidden, okay? So, okay, so we understand these issues. So why don't we just go ahead and directly add encryption at the physical layer and then solve the problem? I mean, why did they add it, at the L2 or higher layers, okay? So in civilian networks, they added it there because it's much easier to do it there rather than at the physical network. There are quite a few challenges associated with that. There is a question of latency. Unlike in the higher layer where you can send something and then you can take a little bit more time, here all the radio frames are all running in real time. So if you send a request, then immediately you have to expect a response at a fixed interval. So all these are time sensitive things which are happening in the physical layer, and if you add encryption, it can add to the latency. And also there is a question of where do you get the keys, right? In case of encryption being at the higher layer, what you will be able to do is still access through the physical layer, do some access procedures and then get the key. But if the physical layer itself is encrypted, then how do you get the keys, okay? Then there is also that when you add things at the higher layer, you are often adding it, on end to end or for a particular user. There is no multiple users to contend with, okay? So that again makes using the keys and other things challenging. So we like just propose a method to do this in a way which solves all these problems, okay? So again, some of the options which people generally take when you want to add encryption to the physical layer is, okay, you got the L2 module and then you got the L1 module. Inside that, why don't we insert a security module, okay? So this is a typical approach taken by many implementations. So one, it actually avoids access to L1. Now L1 is something which it's a complex entity and people don't want to open or tamper on it. They may not even have access to that, and so you can do it at the higher layers just above that. And it's also easy to implement it at a board level solution. If all that you have access is only to design, then this is an approach which could work, okay. But being a chip company which has physical layer capabilities, we thought, okay, now that we have access to this, can we do something better, okay. So one of the things which we realized was that if we push the security module a little bit into the layer 1, okay, right, and see, this would not be possible at least for Indian defense without Indian chipsets, because we do not have access to those chipsets, okay, but because we do have, so we went around this chain of thought, okay. So before we get into the details, very briefly I would like to say that just like other layers, physical layer also composed of different steps, and you can see that the data is coming from L2. There is a channel level thing which is basically manipulating the bits, then there is modulation, and then there is MIMO processing and OFDM, and then it finally goes towards the antenna, okay. This is a very brief channel structure, okay. And if you notice, one particular area in that channel processing is called scrambling, okay. So here the information bits are coming, and then a scrambling code is generated, and these two codes are combined to actually produce a scrambled bits. Now this is already in the standard, but its purpose is not to provide any security or protection. It is simply to randomize the bits which are being transmitted. Why? Because like sometimes, let's say when you have a period of silence, you know, the data which is going around could actually be zeros, or your camera is facing a blank wall or the white sky, it will all be ones, and those kind of things can cause some problems, okay. To independent of the user data, you want some random bits in the actual data being transmitted, so that's what the scrambling is doing. Now the scrambling code is based on the cell's ID, which tower you are connecting to, that tower's ID, the frame number, and few other details like that. But the point is, all this will also be known to anyone who is an attacker. So he would be able to reconstruct the scrambling code, and then he will be able to get it. So its purpose is not at all protection. But if we take it and change it in a secure way, okay, which is what we call as secure scrambling. So that's what we call our method. So what we do is, now in order to generate the scrambling code, you need some other information which is available only with the legitimate users, okay. So what are those? So one is, we will introduce a ciphering key, and we will also introduce some additional inputs. So these are things which go hand in hand with cryptography, because there are certain type of sophisticated attacks, and to prevent that, you not only just need a key, you need some other input. So we'll just leave it at that over here. We will continue to take those previous protocol inputs, okay, and we now have a scrambling code generator which goes to an encryption module, and then what comes out is actually a what we call as a secure scrambling code. And now when you combine this with the information bits, it is equivalent to having the bits encrypted, meaning unless the attacker has access to those keys and other inputs, he will not be able to reproduce it. Now you would notice that we have, and this operation is a very simple operation, okay, and you notice that by just latching on to that and modifying that, okay, we would be able to preserve all the physical layer functionalities, okay, and hence we solve the problem of latency. So this does not add any latency, which was one of the problems which we had mentioned, okay. Now let's also look at the other problems which we talked about. Okay, how about obtaining keys, okay. So again, so we take what is called as the multiple key approach. The multiple key approach, what it says is, first step, you minimize the amount of unencrypted information, okay. So you restrict it to the bare minimum synchronization channels. So if you talk about a fortification, this means that, well, you will be able to know that there is a fort there, but nothing else, right? That's what is the equivalent. And then at each step, we will have a higher level of key, which we will have to obtain to progressively get access to the network. So just by looking at the unencrypted thing, a mobile will be able to get the physical ID and the frame numbers and few other information from the MIB, okay. So then what happens is, then we have a basic key generation process. Now in this generation, these inputs which you have received from the air, along with some things which are there only with the mobile and the user. So this could be SIM card, this could be a key fob, this could be a password, this could be biometric, all those, depending on the level of security, we can have all of these or a subset of these. Now these are also required along with the received information to generate the basic key. Now only when you have the basic key, you will be able to get the next level of, again, a minimum information which is needed to start accessing the network, okay. So now once you have received this and you got this, with that you will be able to actually access the network and do an authentication procedure with the network. Now when you do the first step was done totally offline. You did not have to actually communicate with the network. You have the SIM, you received something passively over the air, and the passwords and keys, it was all done locally. For the authentication, it actually goes into the network and there is a challenge response and other things which are happening, and only the keys which are needed for that user gets generated over there, okay. So in this way, we kind of bootstrap the process of getting the keys, okay. So I think we just covered these type of copies, the basic key for access and then the common key for all the higher layer signaling and the user specific keys, okay. So now we just wanted to, once we had this scheme and then we put it down, and then later on after a few weeks we were wondering, okay, how does it fare against some kind of attacks, okay. So for example, once you have put it, okay, we realized that we could easily modify the scheme to protect against many different type of attacks. For example, we talked about many control channels, right? I also talked about some channels are like the entry channels, and similarly there is another channel which is now these channels actually take a smaller portion of the spectrum, okay. Now by jamming these critical channels alone, okay, you are effectively jamming the whole network, but to jam the whole network you would have had to block the 20 megahertz of channel, which would require a lot more power and which will require a much bigger system. By specifically jamming only these, right, you would be able to effectively jam it efficiently. Now what we see is that once you have scrambled this information, you can very easily disguise the location of these critical channels. So an attacker will not know where those critical channels are, so that he can just single out those critical channels and do an easier attack. Again, so with this, so what we would do is the location of these key channels is also encrypted in the system information. So that's what came out naturally out of this scheme.
You got 1 minute.
Yeah. Okay. So I think I think this is a very simple scheme where you have these multiple user data which is going on, and we would apply a keys to each one of them. Okay, so this is something which comes out again naturally because of the scrambling which you have done. Okay, so we'll skip that and we'll go a little bit into the final step over here. Okay, so how does this compare with encryption at the L1 interface? Okay, so one thing you notice is that the L1 L2 boundary is actually a little bit more complex, whereas this boundary is actually acting on just bit streams. So it's very easy to bring it out and implement proprietary national defense algorithms. That's one. The other thing is, at this level you are also operating on larger number of bits. Why? Because for communication you add and you make some redundancy over the bits. Now you are acting on these larger number of bits. These two gives us some advantage. I just like to stop with this here. But the question that people always ask is, okay, we have this, but is it actually practical to go ahead and implement this? Okay. So this is where what we would like to say is that if you see any system, like it has the core silicon, then the embedded software, then the system hardware, application software, and the hardware and many other things. So this is how it is. Now, so far we don't have the core, okay? So we have been working on things which are outside. Even getting access to some of those are actually sometimes difficult, okay? But if we have access to that core, right? Which is what a system on a chip company like Signalchip and few other India-based companies can do, is that this entire thing is available and it goes into a chip, including the physical layer, and we will be able to implement all these concepts. So again, briefly coming on to, so what does this really give, right? So you have this entire spectrum where you can take a third-party product and then make some modifications and add security. Or you design a product, a complete custom design, right? Based on off-the-shelf components, maybe you are getting a little bit more security. But when you do it based on a system on a chip, that is where you get the maximum level of security, because you have complete control over the entire system right down to the last transistor, okay? So I think to conclude, we'd like to say that, so we have protected this, we've shown the bootstrapping mechanisms, and also this is something which minimizes the change to the existing thing. So with this, we would like to just thank you for the opportunity, and as Professor said, we will take the questions at the end. Thank you.